Hello. In this video, we are going to look at the binomial distribution. The binomial distribution is used to model many discrete probabilities. For example, coin flips. If you're looking to model the probability of getting different outcomes with coin flips, you can use the binomial distribution for that. So for example, let's say you flipped a coin 10 times and you want to know what the probability of getting a certain outcome was. So we could say, what's the probability of only getting one head on 10 coin flips? Or 5 heads? And so on. So any type of outcome that you're interested in, you can go through and calculate the probability of getting that outcome using the binomial distribution. So the binomial distribution cannot be used for modeling every discrete probability distribution, though. So we are going to have some characteristics, some restrictions. So the first one is that there must be a fixed number of trials, this fixed number of things that you're doing, that you're finding the probability for. So in the example that I gave above, we're flipping the coin 10 times. So there needs to be a fixed number of trials. There are only 2 outcomes possible, success or failure. So in this case, if we want to know the probability of getting 5 heads, then heads is going to be a success and tails would be a failure when you're going through and modeling that situation. The probability of the success must be the same for every trial. All right, and then finally, the trials must be independent. So for the example with coin flips, you can see how coin flips do satisfy this. So assuming that we're flipping a coin 10 times, that gives us a fixed number of trials. There are only two outcomes possible. There are only two outcomes possible for a coin flip, either heads or tails. The probability of success is the same for every coin flip. So it's not that you get different probabilities as you flip the coin. It's not like the coin becomes over time as you flip it, the probability of getting a certain outcome changes. Nope, every single coin flip is the same. And then the trials are independent. So what that means is that if you get a head, the next coin flip is like it's reset. So it's not that the head that you got actually affects the next outcome. So that's the idea of being independent. So we covered that in a previous video. The idea of dependence would be if you got a head, then that would change the probability of the next outcome for the coin. That's not the case, and then we need it to not be the case in order to use the binomial distribution. Okay, so the trials must be independent. Let's look at an example. So the example we're going to look at is ESP reading. So when you're tested to determine whether you have ESP, so your ability to extrasensory perception, I believe is what it stands for. It's the ability to go through and read like Zener cards. Okay, I guess let me stick with what the text has, since the text will explain it. All right, so Zener cards are used to test whether someone has ESP. Okay, I guess it's mind reading. Oh, that's what I was like. Is it mind reading? What is ESP? So I'll show you a picture. It's from the text. I can find it. There it is. All right, so the idea is that you have, these are Zener cards, and they're, one of, there are 5 different possibilities. And what somebody does is somebody goes through and they look at a Zener card, and then, so like if you were being tested, and I was testing you, I would look at the Zener card, and then you would try and read my mind to identify which card was that I was looking at. So I'm looking at the card, you're trying to read my mind to determine what card I'm looking at. I think that's right. In any case, the idea is that there are these cards, and you're expected to guess the outcome without seeing the card. All right, so the goal is that you guess the outcome without seeing the card, whether that's you're reading the person's mind or whether you're trying to discern it from some other magical power. Yeah, that's the idea. Okay, so how does this meet the criteria to be binomial? So we've got ESP reading. Zener cards are used to test whether a person can read minds. Oh, and I guess there's a little bit more information here. A person guesses 3 times correct out of 10. What is the probability of this happening? Oh, sorry. What is the probability of this happening, assuming that that it was random? So assuming the person does not have ESP and it was just random. What's the likelihood of getting this outcome just based upon random chance? All right, so that's the question. We're not going to answer that right now. But what we are going to look at is does this satisfy the conditions of the binomial distribution? So could we go through and model this situation using a binomial distribution? All right, so what are those again? Let's take a look. So the first one, fixed number of trials. Do we have a fixed number of trials? Yes, 10 trials. So they guessed 3 times correct out of 10. So 10 trials were done. Are there only 2 outcomes possible? Yes, there are only 2 outcomes possible. Either you guess the card correctly or you don't. So it's one or the other. So there's no shades of gray. 3, the probability of success is the same for every trial. Now, assuming that it's random, okay, which is what we're told, assuming it was random, then yes, the probability of success is if there are 5 different symbols, which is what there were. I don't know how closely you looked when I was displaying the cards, but there are 5 different symbols, and so your chance of guessing correctly, if you didn't know, would be 1 in 5, and it would be the same every single time. It would not change as we went through and did each of the 10 trials. And then finally, the trials are independent. Again, assuming that you do not have magical powers, the trials would be independent. So it's not that if you got 1 card correct, that you'd be more likely to get the next card correct. Assuming it's completely random, then each trial would be independent. Okay, so that's an example, of where we could go through and use the binomial distribution to answer that question, right? So why would you want to answer this? Well, the idea is if you're going through and you're testing somebody and they guess 3 times correct, you want to know, is that, if it was completely random, how likely is that? Because knowing how likely that is would help you to determine, does the person actually have magical powers or not, right? So if you go through and you determine using the binomial distribution stuff, which we'll get to, but let's say you go through and you use that and you determine that 3 times correct out of 10, that happens 70% of the time, or I don't know what it is because I haven't done this one, but then that would not be particularly telling that someone was able to guess 3 times correct. But if you go through and you determine that 3 times correct out of 10 is a really rare outcome, that's actually quite difficult to do, then that's totally different. And so that would imply that the person does actually have magical powers. And so knowing the probability of getting a result is really important for testing, at least in this case, whether the person actually has the powers or not. So that's the benefit. That's the benefit that you get in this case. Okay. Anyway, so the point is, right now we're just trying to figure out what satisfies the binomial distribution criteria and what doesn't. So we'll come back to the ESP question later. Let's look at some examples that do not satisfy. And we're going to want to go through and identify why. So first example, number of different eye colors. In 50 random people. To make this more similar to the previous example, I think this is the language that was in the text, but the idea is that you're guessing eye colors. I think that's the idea, is that you're guessing eye colors for 50 different random people. Why would that not be a binomial distribution? So 2, a couple has children until a girl is born with a max of 5. All right, this one is probability a flight will arrive on time to O'Hare in Chicago is 85%. So let's say you can check this. Probability a flight arrives to O'Hare. So this is, the statistic for year round. The probability a flight arrives is 85%. How many flights are on time out of 300 on a day in January? And then number 4 here, student guesses randomly on 10 random multiple choice questions and 10 true false questions. How many questions are they likely to get correct? So each one of these does not meet the binomial distribution criteria. So why is that? All right, so if you're going through and you're guessing the number of different eye colors, so if you've got different eye colors, then there are more than 2 outcomes. So you can guess, blue or brown, or what other eye colors are there other than blue and brown? I guess there's different shades. Green, there's green eyes. Anyway, there's more than 2 outcomes. And so that's the problem with this, is more than 2 outcomes. So if you go back and look, right, so what are the criteria here? Fixed number of trials, only 2 outcomes, so on. So there's too many outcomes. All right, a couple has children until a girl is born with a max of 5. So which of these does that violate? It's the first one, fixed number of trials. So until a girl is born, so if a girl is born immediately from the first child, then you'd only have 1 trial. Meanwhile, if you don't get a girl right away, then you could have up to 5 children. So not fixed trials. How about this one? So this one got me when I read it. I was like, oh, what's the problem with this one? Well, you gotta read it a little bit carefully to see what the problem is. So the probability of flight to O'Hare arrives on time, I guess I should put on time, is 85% over the course of a year. How many flights are on time on a day in January? Ooh, that's what I missed when I first read it. January. So if you're not aware, there's a lot of inclement weather in January. And so because of that, the outcomes are, for whether flights are on time or not, are not going to be independent from each other. All right, so the probability, so trials, it must be independent. They're not independent. If one flight is canceled due to inclement weather, then probably others are too. So we do not have independent trials. And then finally, see, I think this one is the least obvious of the four. And then finally, the student guesses randomly on 10 multiple choice and 10 true false. So there's only one possibility left, but the probability of success must be the same for every trial. If you're going through and you're modeling and someone has 10 random, so 10 multiple choice and 10 true false, then the probability of getting a multiple choice correct and the probability of getting a true false correct is not the same. And so because of that, we have we have different probabilities of success. And so that doesn't work. All of the trials must have the same probability of success. It needs to be like the coin flips. Here, it's like you've got coin flips here for true and false, and then you've got dice rolls here for the multiple choice, and you can't do dice rolls and coin flips at the same time. So what do we call this? Probability is not the same for all the trials. Okay, and so those are the criteria that you want to think about if you're looking at going through and modeling a distribution. You want to think in terms of, is this like a coin flip? Is it like a die roll? Is it like drawing, I guess the card from a deck, you can go through and do cards from a deck with binomial distributions, but only if you replace the cards. Otherwise, the outcomes would be dependent upon the cards that you previously drew. So we kind of discussed that when we discussed dependency and independency in a previous video. But if you had a card deck with a replacement, then you could go through and model that with a binomial distribution. Same thing goes with like pulling marbles out of a bowl. As long as you have with replacement and you put the marbles back in as you draw them out, then you could go through and you could use a binomial distribution. So that's what you want to think about are you doing the same thing again and again and again and again? Okay. Are you doing it a fixed number of times so you can't go through and like prematurely end? Is every single thing that you do, all these things that you're doing again and again and again, are they independent? So that one outcome doesn't affect the others. And then again, you have to be doing the same thing again and again. So the probability can't change. And so as long as you meet those four criteria, then you can go through and use binomial distribution. All right, so what is a binomial distribution? Let's visualize some stuff. So there's two different factors that affect binomial distributions. So the first one is the probability. With the probability of success for each trial. So if you had like a coin flip and you wanted to, and success was heads, then that would be, the probability of success would be 50%. If you had a dice roll and you wanted and let's say getting a 6 on a dice was considered a success, then the probability would be 1 in 6. And then the second thing is the number of trials. So once you have those two things, you can go through and you can create probability distributions. Let's look at some. Okay, I think this is the one I want. All right, so here's some examples with probability distributions. So the first one we have here is modeling coin flips, where you go through and you do 3 coin flips, right? So you flip a coin 3 times. This models all of the different outcomes that you can get, for the number of successes, right? So if you flip a coin 3 times, and let's say a success was a head, you could flip a coin 3 times and get 0 heads, right? So you could flip it and get tails, tails, tails. So that's one possible outcome. That's 3 coin flips. You get tails every time, failure, failure, failure. So 0 successes. You could flip a coin and you could get 1 head out of 3 results. So you could do head, tails, tails. That would meet this. You could do head, tails, head. That would meet this. You could do tails, tails, head. That would meet this. Those are all different ways that you could end up getting 1 success, 1 head out of 3 coin flips. And then this is 2 successes, 2 heads out of 3 coin flips. And then this is the last possibility, and that is that you get all 3 heads are the same. All 3 results of your coin flips are heads. You get heads, heads, heads. All right, so that's how to read this. This is the number of successes along the bottom. And then the height of each one of these little bars represents the probability of that situation. So the probability that you flip a coin 3 times and get 0 heads, it looks like here it's a little bit over 10%. I think maybe that's 12.5%. But that doesn't matter. It's a relatively small bar. All right, so it's around 10%. That's all that matters, is that you can read that. I believe it's 12.5% though. And then the next case, that you flip a coin 3 times and you only get 1 head, there is just shy of 40% chance of that happening. Okay, you flip a coin 3 times and you get 2 heads. Again, there's just shy of a 40% chance of that happening. And then you flip a coin 3 times, and again, that's the same probability that you get 3 heads is the same probability that you get no heads. And so the probability distribution here models all of the different possible results that you could get for 3 coin flips, and the probabilities are right on the table and makes it right on the distribution, and it makes it easy to go through and read them and identify and understand the way in which outcomes are modeled for coin flips. All right, so that's the idea. That's how binomial distributions work. They model all the outcomes that you could possibly get and their probabilities. All right, so let's say that for the second one, the difference here is that this is a binomial distribution, n is 15. So 15 trials, 50% probability. So we're still sticking with coin flips here. All right, so you flip a coin 15 times, okay? And this models the different outcomes that you could get. So 15 times you could get no heads, you could get 1 head, 2 heads, 3 heads, 4 heads, all the way up to you could get 15 heads. And maybe not, hopefully not surprisingly, the probability that you flip a coin 15 times and you get 0 heads is very, very small. The probability that you get 1 head is very, very small. 2 heads, very, very small. And then the probability begins to rise as you get into these into the middle range. And the probability that you'd get 8 heads, and 7 heads is right here in the middle. So 7 and 8, those are right in the middle. And maybe that's not unrealistic, right? So if you flip a coin 15 times and the probability of getting of each coin flip is 0.5, the notion that you'd end up getting somewhere around 7 or 8 heads is hopefully seems reasonable. Okay, and then as the number of heads rises above that, the probability declines again. And so it's very unlikely that you'd get 13 heads out of 15 coin flips, or 14 heads, or 15 heads. And hopefully that also makes sense. If you flipped a coin 15 times and you got 15 heads in a row, I'd buy a lottery ticket, because that would be insane. That would be very unlikely, a very unlikely result. Okay, so this is modeling coin flips. Now, we're not restricted to coin flips. You can do other probabilities. So we can go through and we can change other things. So, but first, before we do that, the difference between these two is that the number of trials is different. So the probability stayed the same. So one of the things that you can do here is you can change the number of trials, and that will get you a different probability distribution. Now let's look at cases where we change the probability. So we can model probabilities other than 50%. Okay, I think this is the next one. Nope, that is not the next one. That's the first time that's happened in one of these videos where I looked and I could not tell. All right, yep, this is the right one. Apologies for that. So we will get back to that other image in just in a few minutes. All right, so we have a couple more examples. So we have 15. So now we're keeping the number of trials the same, 15, but we're changing the probability. So if you go through and change the probability from 0.5 to 0.3 for 15 coin flips, sorry, they're not coin flips anymore if the probability is 0.3. I'm not sure what would be modeled with 0.3, but it's not a coin flip. That would be a very odd shaped coin. In any case, so we have 15 trials, and now the probability of getting a success has been reduced from 50% down to 30%. So how does that go through and change the shape? All right, so if the probability of success is reduced, so it goes from 50% down to 30%, then that's going to make these low number of successes more likely, right? So if you were to go through, and I'm going to use coin flips just for simplicity of language, but obviously the probability of flipping a coin, unless that coin has been doctored in some way, it's not 30%. But if you flipped a coin and the probability of getting heads was 30%, then getting 0 heads or 1 head or 2 head or 3 heads would be far more likely on 15 coin flips. So as you reduce the probability, it makes the low number of successes more likely. Okay, hopefully that makes sense. Lower probability makes low number of successes more likely. And that makes high number of successes less likely. Okay, and so getting 15, 13, or even 10 successes, even 10 quote unquote heads on a coin flip where there was only a 30% chance of getting heads would be very, very low, much lower than it was when we had a coin flip where the probability was 50%. So high success numbers become less likely. The thing that's interesting about this shape is that it's not symmetric. So that's kind of a fascinating characteristic, is that if you go through and you have a relatively small number of trials, like 15 trials, and you have a skewed probability, 30% or 70%, something other than 50%, then you can end up having a skewed distribution like this, where one side is more likely than the others. But what's really crazy, is that if you go through and you increase the number of trials enough, the distribution eventually does become symmetric. So you just need to have more trials as you have more extreme probabilities. And my guess, without going through and doing this, is that the more extreme the probability, the larger the number of trials that you need to have before you'd have symmetry in the results. So that's kind of a cool facet of binomial distributions, is that you can get skewed results when you have low probabilities or high probabilities, when you have probabilities that are away from 50%, but those eventually become symmetric if you go through and just do more trials. All right, so that's we've kind of talked about visualizing some different distributions. All right, so how about finding binomial probabilities? So what if we wanted to go through and use the probability distributions that we've just been looking at? We wanted to go through and find some of those results, right? So let me just go back and just point out exactly what I mean by that. So this first one, I was saying, I think this is 12.5% right here. And I think this is 37.5% right there. What if you wanted to get that exact value, right? What if we wanted to get these outcomes? I mean, the point of using the binomial distribution is not just to look at pretty graphs. It's to actually calculate probabilities. It's to get these outcomes. So how do we do that? That's the next thing we're going to talk about. So something does satisfy the requirements to be a binomial distribution. You've got a pretty graph that you can look at that gives you the shape of the results. But what you want is you want to know a probability. You want to actually know the results, to the probability of getting, the probability of getting 3 heads on 15 coin flips. You want to know what these actually are. So first, before we do that, before I show you how to do that, so we're going to use StatCrunch for that, of course. But first, we're going to introduce some notation. So that notation, this is the notation for binomial distribution. You put B and then a parenthesis, and you get N, P, X. All right, so the N here is the number of trials. And then P is the probability. And so now, since we're actually looking for a probability for a specific result, right? The example I just was showing you is, that's the probability of getting 0 heads on 3 coin flips. What we need is the last thing is we need to know the outcome that we're looking for. What is the number of successes that we want to know the probability of? All right, so let's look at some examples, and we're going to use StatCrunch to go through and calculate these outcomes. But these are some potential examples. So suppose 5% of bicycles are returned to their 5% of stolen bicycles. I believe that's supposed to be. So suppose 5% of stolen bicycles are returned to their owner. If 235 are stolen, that's a lot. If 235 are stolen, what is the probability 10 will be returned? All right, so how do we go through and calculate this? So we're going to use our good buddy StatCrunch. Let's see here. Which of these windows is StatCrunch? Here it is. All right, so once you've got StatCrunch powered up here, to go through and use the binomial distribution calculator, you want to go to Stat, Calculators, Binomial. All right, so you see that? So just one more time here. So you're going to go to Stat, Calculators, Binomial. And what you've got once you load this is it's got a example binomial distribution that's there. So what it's got is the default here is 10 trials and a 50% chance of success on each trial. So basically 10 coin flips, and it's displaying the probability that you'd get less than or equal to 5 successes. Now, that's not what we're interested in. So let's go through and change the numbers. So the example we just looked at, we said that 235 bikes are stolen. So that's 235 potential bikes that could be returned to their owner. So we want 235 trials. And then the probability that of a bike being returned, we said was 5%. So we want to enter as a decimal 5%. So that's 0.05. And then we're interested in an exact outcome. So you want to go through and change this from less than or equal to. We want exactly equal to. All right. And then we specifically want to know the probability that 10 are returned, exactly 10. So once you've got the number of trials, the probability, the type of type of equality or inequality, and then the number of successes that you're interested in, then you can go ahead and just hit enter or compute. And so this gives us the probability is around 11%, 0.11. So the probability that somebody that 235 bikes are stolen and exactly 10 of them are returned is about 11%. Okay, so that's how we could go through and calculate that result. So you just have to bring up that binomial calculator and enter the information that you're interested in. Right, enter the appropriate values. All right, so in this case, I didn't write it on this previous page here, but what would our notation be? So we'd have B, and then what is it? I think N is first, right? So it goes NPX. So N is 235, P is 5%, so 0.05, and then the number of trials we were interested in was 10. Okay, so that's what we entered. Let's look at another example. All right, so this example is titled recidivism in Texas. So I'm not familiar with that term recidivism, but the idea here is that that they describe in the problem. So suppose you're told that the 3-year rate that parolees return to prison in Texas is about 20%. So this data is from Texas, but I'm too lazy to write that. All right, so suppose 15 prisoners are released. What is the probability 6 return to prison? All right, so let's write out our notation here. So we want to know the binomial probability. How many trials are there? So we've got 15 prisoners are released who could potentially return. The probability that someone returns to prison is 0.20. And then we want to know the probability that 6 return. 6. Okay, and so now we can jump back over to StatCrunch. All right, so now we want to go through and enter the number of trials. What was it? So 15. Probability 20%. We want to know probability of 6 trials. 6. Okay, so the probability that 15 are released and 20%, there's 20% probability that each one returns. The probability of getting exactly 6 is about 4.3%, around 4%. So one other thing I didn't mention this with the last example, but by looking at the distribution, you can put context to the outcome that you got, which is important, right? So we got 6, and so what context can you apply to that? What is that? What can you read into the graph of that result? And that is that 6 is actually a lot. 6 out of 15 returning to prison is really high. How can we tell that by looking at the graph? It's because you have these really tall bars with much higher probabilities, right? Tall bars go with high probabilities. So 6 returning to prison has a really short bar relative to these taller bars. So 5 is more likely than 6, 4 is more likely than 5, and then 3 is where the peak is. So if you had 15 parolees, the most likely outcome in terms of the highest peak would be that 3 return to prison. So 6 is a lot, relative to only 15. So that is something that you can't really tell just by the 4%. So you can't tell, is the 4%, is 6 a small number out of 15, or is it a high number out of 15? You can't tell without actually seeing the distribution. So that's one benefit of being able to see the distribution. All right, let's look at another example. All right, so we're back to the ESP. All right, so we've got our ESP reading. And so someone predicts 10 Zener cards. So again, just a reminder, each card has 5 shapes. So we looked at that earlier. So it's 5 possibilities. That's the way to look at it. What's the probability of getting exactly 5 correct answers? And then we're going to look at a couple others. So we're going to start branching out here. What about 5 or more? What about fewer than 5? All right, let's go through and find those probabilities. Oh, let's actually write those out. Well, we don't have inequalities, but we can write out the 5 case. All right, so we want B, that's for our binomial probability. How many trials do we have? 10. What's the probability of success? So it's not given to us. However, assuming it's random, like you actually don't have ESP, and you're just randomly guessing, then you have a 1 in 5 chance. A 1 in 5 chance. You could actually even write that if you want to, 1 in 5. But you want to turn this into a decimal at some point. So you want to take 1 and divide it by 5. And so you're going to get 0.2. That's 1 in 5. And then we want to know the probability that 5 are correct. So 5 is the last value here. Okay, so let's go through and calculate that. Bring up our stat crunch here again. Let me just check something just to make sure. Okay, I was just making sure that you could see the graph here. All right, what are we doing here? So we got 10 trials. 0.2 is still the result we're interested in. And then 5, we want to know the probability of exactly 5. So you go through and you don't have ESP, you guess randomly, for 10 cards and you get 5 of those correct, there's about a 2.6% chance of that. That's really unlikely. All right. So if you were to go through and guess, and you were able to consistently do this, you're able to consistently get 5 correct out of 10, then you got ESP. you can read minds, or whatever ESP means. So this is going to be, what did we say? This was about 2.6, was it? 2.6%. So that's a pretty unlikely that you'd be able to get. Yeah, it was 2.6. Pretty unlikely you'd be able to get that correct. All right, so the next part says 5 or more. 5 or more. So we want to find the probability. So we want to find the probability that you'd get 5 Or so 5 or more is 5, 6, 7, 8, 9, and 10. So how do we do that? So what you could do is you could do equals 5, equals 6, equals 7, equals 8, equals 9, equals 10, and go through and add all of them up. You could do that. Or take a look here. If you go ahead and click on this, on the equal to here, it's got some options. It's got less than or equal to, greater than or equal to, less than or greater than. All right, so if we say 5 or more, then what does that mean? That means 5 satisfies the inequality. So we would want 5, we would want equal to, and then anything above that. So we're going to want greater than or equal to for 5 or more. And so all you got to do is just change this, and the probability should change. Ooh, and it went all the way up to 3.3. So the probability of getting 5 or more correct is not a lot higher than the probability of getting 5 correct. And that's the reason for that is just the probability of getting 6, 7, 8, 9, or 10 cards correct when there's only a 20% chance for each card is just extraordinarily unlikely, right? It's just very unlikely that you'd get more than 5. Even 5 is only 2.6%. So one thing that the text that we're using really stresses is the difference between 5 or more and more than 5. All right, so if we were asked to find the probability of more than 5 does not include 5. And so you do need to be careful if you've got 5 or more versus more than 5. If the question had been, what's the probability of more than 5, then you'd want to use the greater than without the equal to. And then suddenly you get a different result. Okay, so let me just kind of put a little note about that on this page just to kind of, we've got 5 or more versus more than 5. So you got to be careful here language-wise with the language, and that is the number that they give you, is that included? So you want to use the equal to as part of it, like greater than or equal to, or less than or equal to, or is the number not included? And if you see something that says, what's the probability for more than 5 does not include 5. All right, so this one would be greater than or equal to versus this one, which is just greater than. All right, so you do need to be careful of that between those two, because you do get different probabilities. And so speaking of that, the next one is, what's the probability of getting fewer than 5 correct? So fewer than 5. All right, so we could go through and calculate that. All right, so fewer than 5, that does not include 5, right? It would say 5 or fewer if 5 were supposed to be included. So fewer than 5, we're going to want just the less than without the equal to. And if you just change it like that, that gives us fewer than 5. And that probability is about 96.7%. And one of the things if you're thinking about it, you'd be like, wait, is that the complement of 5 or more? Absolutely, right? If you took the probability of getting fewer than 5, that's the probability of getting 4, 3, 2, 1, or 0. 5 or more is 5, 6, 7, 8, 9, 10. Those are complements. Those are opposites. All right. So, the just as something to keep in mind is the complement information that we've learned earlier in the semester. Okay, I think I have some pictures for this. Okay, yep. So what we've got here is we've got the picture distributions from the text. And so what they show is they show the probability. So you got 10 trials. That's 10 times you're picking cards, 20% probability that you get it correct. This is what the distribution looks like. And then we can go through, and 5 or more would be, there's 5, there's the probability for 5, there's 6, 7, 8, 9, 10, and you add all of those up, and you ended up getting, I think it was like 3.3%. All right, and then so here we've got the complement of that. Here's n equals 10, 20% probability. You getting fewer than 5. Fewer than 5 does not include 5. So we're going to get 0, 1, 2, 3, and 4. And if you add all of those up, you get the opposite. So 96.7%. It's like the opposite of 3.3%. And then they give you a nice little picture here at the bottom that shows that these are complements. If you've got fewer than 5, that goes from 0 to 4. 5 or more goes from 5 to 10. Those are all the possibilities. And so if you add them together, you get 1. And if you add 2 things together and get 1, then that means the 2 things are complements. They are opposites. Okay, and they even say that. Boom, complement of 5. Okay. There's more to this section. Let's go back to our whiteboard. One of the cool things, I think this is cool, that you can do with binomial distributions that you can't really do with continuous distributions is since binomial distributions have a finite number of outcomes, right? We've been looking at them, 0, 1, 2, 3, 4, like the last one we just did from 0 to 10. Because of that, you can go through and take those outcomes and you can calculate the mean and you can calculate the standard deviation of those outcomes. All right, so since there are finite outcomes, I'm just going to write down what I just said. So since there are finite outcomes, we can calculate a mean and a standard deviation. And I've got a picture for that. Yeah, this is the one that I briefly showed earlier. All right, so we can see. So right here, we've got a distribution, one of the first ones we looked at, 15 coin flips, right? And so if you take a look at that, that is perfectly symmetric, where we have the middle of our distribution has 2 equal sized bars, and so the mean is going to be directly between them, right? So if you just look at this, this is the bar for 6, 7, 8, 9, 10, and so this bar here, this outcome was at 7.5, right? So if this one is at 7 and this one is at 8, and we're calculating the mean, and the mean is going to be directly between them, then that's going to be 7.5. One thing I should clarify here is that the mean is the same mean that we've always done. So we're going through and finding the balancing point of the distribution. Okay, that's how it works. All right, and so you can go through and use the mean. And so if you look at this, you'd be like, oh, wait, but it's skewed. Shouldn't we use the median? It's pretty symmetric-y. All right, so yeah, it's got a little bit of skew, but it's okay to still go through and use the mean when you have a little bit of skew. And the amount of skew that these probability distributions are going to have is going to be small enough that we can go through and use the mean. That doesn't mean that the skew doesn't pull the mean to the right, because we're skewed to the right, just like it did with earlier examples. It does exactly that. The skew does pull the mean in that direction, but I mean, you can still go through and calculate it. And what does it say here? The mean is at the balancing point. So it's around 4.5. Yes, the balancing point is around 4.5 in this case. So if you've got 15 trials and the probability of success is 30%, then you're likely to get, then the mean result, hold that likely to get thought for just 1 second, then the mean result is going to be 4.5, right? So for these are somehow our weighted coin that only gives heads 30% of the time. If you flip a coin 15 times and the probability of getting heads is 30%, then the mean is 4.5. I keep want to use that likely to get language because that's the next thing we're going to talk about. All right, so how do you go through and interpret the mean and standard deviation? All right, so I apologize. So first we're going to do the formulas. So what are the formulas? So the neat thing about going through and calculating the mean and the standard deviation for a binomial distribution is that you don't need to go through and use StatCrunch to do it. You don't need to, go through and list all the outcomes and calculate the mean, using, by adding all of them up and dividing by the number of outcomes. Instead, there is a shortcut formula. This is pretty cool that this formula exists and that it works. All right, so if you can go through and the mean, we're using mu here, equals n times p. So that's times. All right, so you take the number of trials and then you multiply by the probability. Okay, and that enables you to go through and get the mean. That's it. So all you got to do is just take the number of trials and the probability, multiply them together, and that's going to get you the mean. All right, and that's still the balancing point, just like the previous examples for the way that we define mean. It's the exact same mean that we've used all along, same definition, just a new fancy shortcut formula that only works for binomial distributions. So don't use this on anything else. All right, and then the standard deviation. So this is for the mean. And then there is a cool shortcut formula for the standard deviation as well. That is equal to the square root of n, which is the number of trials, times p, which is the probability, times 1 minus p. All right, so 1 minus the probability. And again, this is the same old standard deviation that we've talked about all along, that we've used in the past. So the standard deviation, still, we can go through and do all the same stuff that we've done with standard deviations in the past, with going through and using the empirical rule and, counting the number of standard deviations and the way in which the data should be distributed based upon those standard deviations. All of those things, all of them still apply. Okay, so this is the same mean, balancing point, same standard deviation with the empirical rule. It's all the same stuff we've done before, just fancy trick formulas that we can go through and use to calculate these much faster without having to go through and do them by hand. Okay, and so I kept saying likely result. So one of the most important, one of the most powerful results that you're going to get out of this is what's called the expected value. So you'll hear this used in statistics fairly regularly, or statistical contexts. You'll hear things like the expected value. So the idea is that if you flipped a coin 100 times and the probability of any individual success was 50%, then the probability, then the expected number of outcomes, the expected number of heads that you're going to get, you can find by just multiplying the two numbers. So that's a very important result. So expected value, you hear that pretty regularly. And so you do want to understand what that means. So this is interpreted as the expected number of successes. when performing, we're going to call it an experiment. But what that means essentially, it means the things that we've been looking at. Like if you're going through and you're flipping a coin 15 times, then that's the experiment that you're doing. If you're going through and you're having someone draw 10, the ESP cards, what were they called? Xenox or something? Zener cards. And so if you put all the trials together, then we're going to call that an experiment. Okay, so the expected value is the same thing as the mean, and it's interpreted as the expected number of successes that you'd get when performing an experiment. So let's look at some examples just to make sure that everything is clear what we're talking about. So if you flipped a coin, it's flipped 100 times. What is the expected number of heads? All right, so to go through and find that, what you do is you take the number of trials. So you're doing 100 coin flips, and you take the probability of getting heads on an individual coin flip, and you multiply by it. So you're going to multiply. So the probability of getting heads on an individual coin flip is 0.5. And so the expected number of heads is 50. And that's it. All right. So that's all there is to it. And intuitively, it kind of makes sense. So if you think about flipping a coin 100 times, if the probability of getting heads on any one time is 50%, then you'd expect that you'd get 50 heads out of 100 times. So if you went through and did this, you'd expect that you'd get 50 heads and 50 tails. That would be your expected. That's not. I'm not saying that that's exactly what you'd get. The whole point of expected value is what you would expect. It's what you would guess that you would get. So if you actually flip a coin 100 times, you may get 50, or you may get 51 heads, or you may get 52 heads. You may not get exactly 50, but before you actually do the flipping, if someone is like, what do you think is going to be the outcome? Well, if you do 100 coin flips and each individual coin flip gives you a 50% chance of getting ahead, then you think you're going to get 50 heads. All right. Just think about that. Right. So that kind of makes sense. If you roll a die, is rolled 120 times, how many sixes would you expect? So how many, what would be your guess as far as how many sixes you'd get? Well, to figure that out, you take 120, and that's the number of trials you're doing. And then what's the probability of getting a 6? Well, if you roll a die, there are 6 things on the die, and only one of them is a 6. And so 1 out of 6 is the probability of getting a 6. And then you multiply those and you get 20. So if you rolled a die 120 times, your guess as far as what you'd get would be 20 sixes. You'd think you'd get 20 sixes. All right. If a card is pulled from a deck, $52 times. This is with a replacement. So you put the card back in after you're done. What? Or sorry, how many? I use the same link. How many times will you think that you'd get which one did I do here? Ace of clubs. How many ace of clubs do you think you'd get? Well, if you pull cards from a deck 52 times, and there are, how many ace of clubs are there? There's 1 out of 52. So you would expect that you'd get the ace of clubs once. Now, does that mean you would get the ace of clubs once? No, that doesn't mean that. The whole point is this is what would you expect would happen? What would your guess be before you actually did the experiment, before you actually took a card, took 52 card deck, pulled a card, looked at it, is it the ace of clubs? Yes or no? And then put it back in, shuffled, pulled a card, looked at it, put it back in, shuffled, pulled a card. You did that 52 times. You would guess that you'd get the ace of clubs once because there's one ace of clubs out of the 52 cards. Okay, so that's the idea of expected value. It is used a lot. It's one of the more important, maybe not about important, but certainly one of the more popular things that comes out of the class. Okay, and then where I think this gets really cool is that these are all, you can go through and we're kind of going back and forth here in terms of interpreting expected value as the mean and then not as the mean. So you notice that on this page, I barely use the word mean at all. I actually don't even think of it as the mean. I think of it as the expected value, but the expected value is the same thing as the mean. And so because of that, we can use our results from the empirical rule earlier in the semester to actually look at ranges of outcomes and the likelihood of getting ranges of outcomes from an experiment. So you may not, that may have been too wordy. So let me show you what I mean by that, right? So if you flipped a coin 100 times, your guess as far as how many heads would be that you'd get 50, right? But what if we wanted to go through and refine that guess by going through and using the empirical rule? Like if we wanted to go through and be able to say, what 68% of the time, what is our range of outcomes going to be when we flip a coin 100 times? So let's say you flip a coin 100 times, you write the result down, you flip a coin 100 times, you write the result down, how many heads, and you just do that a bunch of times, 68% of the time, what's going to be the range for your outcomes? We can use the standard deviation and the empirical rule to figure this out. Watch this. This is cool. All right. So what we've got is we've got 100 coin flips. There's a 0.5 chance of heads. We said the mean was going to be 50, which is 100 times 0.5, which is 50. This is the expected value. That's the result that we expect. Then watch. We can also go through and calculate the standard deviation. The standard deviation is the square root 100 times 0.5 times 1 minus 0.5, which equals 5. And so this is like the standard deviation for the expected value. And the way that we can use it is we can use it exactly the way that we used means and standard deviations earlier in the semester in the empirical rule section, in that we can take our mean and we could subtract this. So we could do one standard deviation range would be from 50 minus 5, 45. Hold on, let me do this. From 45 to 1 to add that, to add the standard deviation to the mean, 55. Did it again. So one standard deviation range for, in terms of the spread of our outcomes, if we went through and did this 100 coin flip experiment, we would get a one standard deviation range would be between 45 and 55 heads results. Okay, and using the empirical rule, we know that 68% of the time, our outcome should be in this range. So that comes from the empirical rule section that we did earlier in the semester. You could do 2 standard deviations. If you do 2 standard deviations, you get from 40 to 60. And then 95% of the time, our outcome is in that range. All right, so in terms of interpreting what we've done here, so you've got 100 coin flips. You actually do the coin flips. You do them 100 times. You flip them. You count how many heads you get. Your guess is that you're going to get 50, but that's not a guarantee. That's your expected value. Instead, you could get 51 or 52 or 53, or you could get 47 or 46. You could get a range of possibilities if you actually did this. All right, so you can go ahead, you can do it. Take a coin, flip it 100 times and count the results, okay? And your guess is that 68% of the time when you do this, if you break out a coin and you actually do this, 68% of the time, your results should be in this range. All right, your results should be between 45 and 55 coin flip results. Okay, and then if you, but sometimes you're going to be outside that range. Sometimes you're going to flip a coin 100 times and you're going to get 57 heads. You're going to get 58 heads. It can happen. There's no guarantee. You could flip a coin 100 times and you could get 100 heads. That's possible. Not very likely, but it's possible. And so a higher probability, a higher likelihood is for the 2 standard deviation range. 95% of the time, or there's a 95% chance that your number of heads is going to be between 40 and 60. Isn't that cool? That is amazing. So you can go through and take this idea of expected value and you can extend it out to add, whatever you want to look at. You could look at this as 68% of the time, or there's a 68% chance. Either one of those are the same way as interpreting this result. And so you can go through and you can do this with the other examples. So I went through and did it with the dice roll. So you've got the die roll, right? So we're rolling a die, 120 die rolls. That just sounds weird, but I guess that's right. 120 die rolls. There is a 1/6 chance of getting a 6. Then our expected value is 120 times 1/6 equals 20. And then you can go through and calculate the standard deviation. That's the square root of 120 times 1/6 times 1 minus 1/6. And assuming I did this right, I got about 4. It's not exactly, but about 4. And so what that tells you is if you roll a die 120 times, okay, you're going to take your standard deviation, you're going to subtract it. We're going to get 1 standard deviation. You're going to get from 16 to 24. All right, and what that means is that 68%, there's a 68% chance, if you actually did this, there's a 68% chance that your result is in that range. 68% chance in that range. Or if you like the other interpretation, because these are the same, 68% of the time, your result is in that range. These are the same. And you could do 2 standard deviations, right? And then we would get from 12 to 28 60s, and that's going to be 95%, same thing. All right, so that's really cool. I think that's really cool. And then let's just finish up with one more example here. So this example, in 2018, Stephen Curry made 92% of his free throws. Oops. He made 92%. All right, if Steph shot 600 free throws, how many would he make, give or take? All right, so someone, by the give or take here, they're looking for a range. All right, that's not exactly maybe necessarily outcome, but necessarily obvious, but that's what they mean. All right, so the expected value, the number you would guess he would make if you had to guess a single value would be, you take the number of times he shot a free throw, and you'd multiply it by his chance of making a single free throw. And so you get 600 times 0.92, which is 552. All right, and then the standard deviation would be the square root of 600 times 0.92 times 1 minus 0.92. Which is about 6.6. And we're just going to round that up to 7. We're going to round up to 7. All right. And then so what you could do is if someone says, how many did he make, give or take? You could say, you know, there is a 68% chance he would make between 545, which is 552 minus a standard deviation, and 559, which is 552 plus a standard deviation. So how much would he make, give or take? He'd make, give or take, between 545 and 559. You know, with give or take meaning, you know, 68% of the time he's in that range. And so that's how you could go through and use the expected value and standard deviation. You could break that out as a party trick, right? So I'm sure you'd be really popular at the party. Someone says, Steph made 92% of his free throws. How many would he make, give or take, out of 600 shots? You could break out a piece of paper and you could say, he would make around 545 to 559. And then everyone would say, you are brilliant. You are amazing. When they're done laughing at you. All right. So anyway, that's the video. Thank you for watching, and I'll see you next time.